Our second example then for max min, on this one, a company wishes to can their juice in a cylindrical container with a capacity of 250 mils. Determine the dimensions to minimize the amount of packaging. So first thing, always draw a diagram. We have a cylinder. What factors are involved in a cylinder? What measurements do we always work with? Well, we have a radius and we have a height. So at that point, that's all we can do for the diagram. Next is the constraint equation. What has to be true about this cylinder? What has to be true? At the end of the day, it has to have a volume of 250. So we know the volume has to equal 250 mils. So what is the volume formula for the cylinder? We know volume equals pi r squared h. We know that 250 has to equal pi r squared h. So again, leave a line here because we're going to have to rearrange that equation to solve for one of those two variables. So stage 3 is to come up with the optimization formula here. So what is our optimization formula? So determine the dimensions that would minimize the amount of packaging. So that is surface area. So that is what we are working with. So what is the surface area formula for a cylinder? 2 pi r squared plus 2 pi r h. So I'm looking at the equation now, and I want to get rid of one of the dimensions, so either an r or an h. So when I'm looking at it, I see that in the first term here, there's no h, and then there's only one h there. So I'm going to replace h from my constraint equation. So returning back to stage 2, I'm going to write h equals 250 over pi r squared. So I just rearrange that equation. So that means my surface area formula becomes 2 pi r squared plus 2 pi r brackets 250 over pi r squared. Doing some simplification, the r in the numerator will cancel. So we end up with 2 pi r squared plus 2 pi 250 over pi r, and I guess I missed that in the previous one, but also the pi's will cancel. So in the final stage then, 2 pi r squared plus 2 times 250, that's just 500. And I'm going to write the r with a negative exponent. So I'm using our negative exponent rules from grade 9 because now I have no fractions, and it's just going to be a straight power rule with the derivatives. So now I'm going to optimize. This is the equation I'm optimizing, and I'm optimizing surface area with respect to our radius. So we're taking the derivative of our radius, or with respect to radius. So this would become 4 pi r plus, oh, well, I'll leave it for now, plus negative 1, 500 r to the exponent negative 2. So I'm going to let the derivative of the surface area with respect to radius equals 0. So 0 equals 4 pi r minus 500 r to the negative 2. I'm going to rearrange the equation. So I'm going to move the 500 to the other side, and now I'm going to rewrite the r with a positive exponent. So that means it would be in the denominator, and it's equal to 4 pi r. Getting rid of the fraction, multiplying the r squared up, so we end up with 4 pi r cubed. Solving for r, it would be the cube root of 500 divided by 4 pi. And that would be measured in centimeters, because we're dealing with milliliters there. All right, so that last step, I divided both sides by 4 pi. I took the cube root. So there is my radius for the new package. How do I find the height? I return over here to my constraint equation. Height is equal to 250 over pi multiplied by the cube root of 500 over 4 pi That's squared centimeters. So therefore, the dimensions will be radius is equal to the cube root of 500 over 4 pi centimeters, and the height is equal to the 250 over pi bracket cube root 500 over 5 pi squared centimeters. So there's your exact value of the dimensions that will provide 250 milliliters of space and volume, and at the same time will provide you with the least amount of material. So anyone that's going into a field of business, this is one of the derivative applications that give you dimensions that you need to package, so you want to make sure that the object is a nice shape so you can optimize your packaging. You don't want to waste money in a business on wrapping materials. All right. Next example, determine the dimensions of a cylinder that will fit in a sphere with a radius of 10 centimeters and optimizes the volume of the cylinder. So you're asking, why would you do this? And my answer is, why not? Why would you not want to put a pop can inside a ball? Seems silly not to want to do that, really. But so there we go. So we put our cylinder inside the sphere, and you can tell by my fantastic artistic ability here, that looks exactly like that. What information is provided? The sphere has a radius of 10 centimeters. So there's the radius of 10 centimeters. We want to optimize the volume of the cylinder. So stage 1 picture, and that picture we're going to revisit it because it becomes very important for us. Stage 2 is the constraint equation. So our constraint equation here is simply the radius of the sphere is 10 centimeters. Now, how does that play a role in the cylinder? So we got to go back a step because we know, or I guess we could go forward a step to show what's going to be important here. So we're looking for optimizing the volume. So we want to find the maximum volume of that cylinder. So the volume of a cylinder, again, volume equals pi r squared h. Now we got to be careful here because this is real radius of the cylinder and height of cylinder. Not that there's another height for the sphere. So we need to find or translate this constraint to relate it to radius of the cylinder or the height of the cylinder. So how do we do that? Well, we have to return back to the diagram. You'll note that it's probably habit that we write the radius of the sphere from center to either the right or the left side. If I was to have written the sphere radius like this, it changes things significantly for us, because now it's a measurement from the center of not only the sphere, but the center of the cylinder to the edge of the cylinder that's touching the sphere. We can then construct a right angle triangle. And that right angle triangle helps us immensely, because this dimension here on the right angle triangle is the radius of the cylinder. This distance here from center to there is actually height of cylinder. So what ties us together here? What is the constraint equation? It's our good old buddy Pythagoras again, and the Pythagorean theorem, a squared plus b squared equals c squared. So we know that the radius of the cylinder squared plus, oops, hopefully you're sitting there thinking he's crazy, height of the cylinder, that's actually only half the height, right? Center of cylinder, that would only be half the height, so I do apologize. At least I caught it this time before I went through and did the entire question. And 10 squared. So we're going to get rid of the brackets. So the radius of the cylinder squared plus 1/4 the height of the cylinder squared is equal to 100. So now we have an expression, a constraint equation that has RC and HC in it. Now we're going to go in, we're going to figure out, well, which one do we want to get rid of or solve? I'm going to rearrange it to for r squared, because r squared is in the equation, r squared is easily isolated, so it just makes the most sense for myself. So radius of cylinder squared equals 100 minus 1/4 height of cylinder squared. So that's what I'm going to substitute in. So volume equals pi. That becomes 100 minus 1/4 height of cylinder squared multiplied by height of cylinder. Using distributive law there, we end up with 100 pi height of cylinder minus pi over 4 height of cylinder cubed. And now we're going to take the derivative to maximize here, derivative of volume with respect to the height. That would leave us with 100 pi minus 3 pi over 4 height of cylinder squared. And now from this point you go on autopilot. You set the derivative equal to 0. So 0 equals 100 pi minus 3 pi over 4 height of cylinder squared. Isolating for height of cylinder, 3 pi over 4 equals height of cylinder squared. Work with me here, dumb board. 100 pi. The pi's cancel out. I'm going to multiply the 4 up, divide by 3. So height of cylinder squared would equal 400 over 3. Or the height of this cylinder would be the square root of 400 over 3. And we're working in centimeters. So again, without a calculator, that's where you would leave it. So now you have a height of the cylinder. All right. And did they want full dimensions in the question? Determine the dimensions of a cylinder. So yep, so now we got to finish it off. So we turn over here, and actually, I'm going to use this line in my substitution because you see that that's what h squared is equal to, and I need an h squared anyway. So that would mean that the radius of the cylinder squared would be 100 minus 1/4, 400 over 3. So taking the square root of both sides, 100 minus 100 over 3, which is just the square root of 200 over 3 centimeters. So therefore, the dimensions would be a radius of root 200 over 3 centimeters and height of root 400 over 3 centimeters. All right, there you go. So that finds you the largest possible cylinder that you can, volume-wise, that you can put in a 10 centimeter radius sphere. Always wanted to know that, I'm sure. All right, so again, moving on to the next video, just continue working through a series of examples. I have one more example in the next video that will allow you then to go ahead and do your work on the max mittens.